Inheritance is an important concept that enables a lot of techniques that we use in C++. It is also the mechanism for dynamic polymorphism, which is one of the staples that allows us to think about design of our systems in very abstract and elegant ways. Largely speaking, we distinguish between two types of inheritance: the implementation inheritance and the interface inheritance. So let's talk about these. How interface inheritance enables abstract object-oriented design, and why we mostly don't use the implementation inheritance. Essentially, we mostly care about inheritance because it allows us to invert dependencies between our components. You might have heard people talking about this as, well, the dependency inversion principle. This term might sound a bit scary, but the concept under the hood actually makes a lot of sense. So let's look at what it really means by following a small example. Imagine that we have a class image that represents its pixel values as a std vector of colors represented by a class color. For the sake of this example, it also has a constructor and a save method that both make use of another class, JPEG.io, that allows us to read and write image-like data in JPEG format. We skip a lot of details of the implementation because we only want to showcase the dependency inversion principle here. Now we can say that the image class depends on JPEG.io class, because image uses the functionality of the JPEG.io in its implementation. We can also think of this in terms of their public interfaces. If a read or write function of the JPEG.io class changes, we will have to change the implementation of the image. But if just the public interface of the image changes, no changes are required on the JPEG.io side. Such a dependency in itself might be completely okay if there are no changes expected from a system that we are designing. And while it does happen sometimes, requiring that there would be no changes in the whole future lifetime of a system is a very strong requirement. And as such, it is also the one that rarely holds. It happens often that systems actually need to change, and even for the most experienced folks, these changes are hard to anticipate. We're just not that good at predicting the future. As an example of one such change, it is absolutely conceivable that we might want to replace the JPEG.io with another class, like PNG.io, that allows us to read and write images in a PNG format. Furthermore, we might need to be able to change the I/O strategy used in the image class at runtime, allowing to pick the one that we want in any particular situation, based, say, on user actions. Currently, to allow for this, we would have to rewrite the image class and even change its public interface to depend on more I/O components, which would make our design quite rigid and brittle at the same time. Add on top of this the fact that different components of complex systems are often developed by different people or even different teams, which makes propagating changes even harder, and we start getting the feeling why we often want to avoid this type of strong interdependency between the components. Dependency inversion allows us to avoid all of these pitfalls. Instead of requiring the image to rely on PNG.io or JPEG.io directly, we can make all of these classes rely on an agreed-upon interface, say I/O interface, thus inverting the dependencies. There is no path along the lines in our diagram from image to JPEG.io or to PNG.io anymore. Here, the image class calls the public methods of the I/O interface, while the JPEG.io and PNG.io classes implement this interface. Coming back to the code, our image now receives a reference to an I/O interface rather than a concrete implementation. Once we design the PNG.io and JPEG.io classes to implement the I/O interface, we are able to pass them interchangeably in place of the I/O interface reference. Look how easy it is now to change the behavior of our image without changing its code. We just pass a new strategy, meaning one of the classes that implement our I/O interface, and it magically works. And if we would want to work with some other image type, we could just add another class that implements I/O interface and pass it instead. Neat, right? In addition to all of this, as long as we designed a good interface, which to me is arguably the hardest part of designing software, we can make changes to the JPEG.io, PNG.io, and image classes independently from each other, as long as they communicate exclusively through the I/O interface. So in the end, we really care about inheritance because it is necessary for this form of dynamic polymorphism, which, along with encapsulation, enables the object-oriented programming, or OOP. And just to make sure we're on the same page, polymorphism stands for having multiple forms. In our case, the reference to an I/O interface can have multiple forms: JPEG I/O, PNG I/O, or any other implementation of this interface. As you have undoubtedly noticed, I have not provided any implementation for our I/O strategy classes just yet, as we only cared about the why here, not the how. We will of course fill all the details in towards the end of this lecture. And for that, we'll need to take a step back and see how inheritance works in modern C++. Because to achieve the behavior we've just seen in C++, we need inheritance. Now, those of you who were careful to follow the lectures on templates might get a feeling that, design-wise, something similar should be possible to achieve using templates too. And you are right. We can do it with templates at compile time, but not at runtime. Depending on our goals, this might be more or less suitable for our needs. So to cover the runtime path, today we focus on dynamic polymorphism and how inheritance enables it. We'll start talking about inheritance by talking about its simplest form, the so-called implementation inheritance. It is designed to simply extend one class, say base, with another, say derived. We say that derived class inherits from a base class, which implies that any object of the derived class contains a full copy of the base class, including all of its methods, appending the data of the derived class to the data stored in the base object. Let's show it on a simple example, as we always do. Let's say we have two structs, base and derived, that inherits from base. We show the inheritance by a colon symbol after the name of the derived class, followed by the name of its parent class, along with some access modifiers, here public, but more on that later. These classes have their corresponding methods, base method and derived method, and some data, which we keep public here for illustration purposes. They also each have a function do-something with the same signature. We then create an object of the derived class and call both base-specific and derived-specific methods on it, as well as print the address of data it contains. Looking at the output this code produces, we see that we can call both the base-specific and derived-specific methods on an object of derived type. Furthermore, because we work with an object of the derived type, the do-something function shadows its counterpart from the base class. As for the data, looking at their address, we see that the derived defined data follows right after the base defined one. Now is probably a good time for a relatively short interlude about access control in classes when inheritance is at play. Before, we talked about private and public access to class methods and data. There is one more access modifier to think of: protected. It works just like private for anybody trying to access data from the outside of the class hierarchy, while within the class hierarchy the data is accessible. That all being said, the core guidelines recommend to avoid using protected data, so please be mindful of this. You might have also noticed that we used exclusively the word public after the colon symbol when using inheritance, but we could also technically use protected or private there. The difference is the following. Using public inheritance maintains the access levels of all data and methods of the base class. It mimics an is-a relationship between classes. Arguably, this is the relationship we mostly want to achieve. Using protected inheritance makes all the public attributes of the base class protected and leaves its protected and private members as is. Finally, using private inheritance makes all the accessible members of the base class private, meaning invisible to anybody, including its own descendants. All in all, we mostly use public inheritance, and the reason is that composition usually is more readable and less error-prone, while achieving the same things as private and to some degree protected inheritance. It makes sense if we think about it. Storing an object of another class achieves nearly the same as inheriting privately from such a class. In both cases, we can access that other class while not exposing any of its data or methods to the outside. The main difference is that with composition, we only can access the stored object's public interface, while inheritance also gives us access to the protected part of the class we inherit from. As a small example, if we wanted to implement a class that would store just integer numbers by reusing the std vector int implementation, we could go either by privately inheriting from std vector int and exposing its base pushback method, or by using composition and having a data member of type vector int, which would require us to implement our own pushback function. I believe that people are split on this issue. Some argue that private inheritance is superior here, as it allows us to avoid boilerplate code of re-implementing existing functions that are already implemented better than most of us can implement them in the first place. While the other argue that composition is superior instead, as it gives us more control and keeps things a bit more explicit. I, for one, lean closer to the second group. But please tell me what you think. Which way do you prefer, and why? Anyway, in the remainder of this lecture, we will assume that whenever we mention inheritance, we actually mean its public flavor. Now, one of the defining features of how inheritance was designed in C++ is that a pointer or a reference to any derived class can be implicitly converted to a pointer or a reference of the base class. This is commonly called upcasting. Up referring to the dependency diagram usually shown in such a way that an arrow points from derived below to base above. Let's see how it works by changing our main function in our implementation inheritance example. We can add a base reference that will point to a derived object. And of course, we can call only base-specific methods on this reference. While this is quite neat, it does not really bring us much closer to our goal of being able to abstract the implementation away behind a pointer. You see, the base reference forgets that it was created from a derived object, and so the doSomething method calls its base implementation. So such simple inheritance is quite limited. To actually be able to define and implement an interface like the one we talked about before, we will need to use virtual functions. But before we do implement such an interface, I want to briefly mention some legitimate uses of implementation inheritance. The only real-world examples that come to mind are the implementation of various type traits and maybe the curiously recurring template pattern, or CRTP. I will not focus on CRTP here. It's a bit of an arcane knowledge, but feel free to read up on it by following the link in the description to this video. But the usage of implementation inheritance in type traits is quite common, and I'd like to briefly look at it here. So I would like to turn to a small piece of code we wrote when we talked about type traits before. This code shows our custom implementation of the std_is_integral type trait that checks if a type provided to it represents integer numbers. Such primary pattern implementation is perfectly fine, but if we look at the standard library implementation, it actually is implemented differently, through inheritance. You see, there is another trait, std_integral_constant, which furthermore has std_true type and std_false type specializations. The std_integral_constant trait already has a static member value defined with all the current best practices in mind, so why not reuse it? And we can reuse these already defined type traits by using implementation inheritance. Here we inherit our struct isIntegral from the false type base class. This has the effect that our isIntegral struct gains the value that holds false. And likewise, we can now specialize our struct for any type we want to be marked as integral type, using another type def, true type. This is really the only use case in which implementation inheritance is routinely used in modern C++, at least to the degree of my knowledge. But if you know of other common examples, please tell me what they are in the comments. Now that we know what implementation inheritance is useful for and what its limits are, we can focus on what we really want, which is to enable dynamic polymorphism, to make sure that when we call a function through a base class reference or a pointer, a correct function from a derived class is called depending on which type in the class hierarchy was used to create the base object reference or pointer in the first place. For that, we have to use the keyword virtual when declaring our base function and override when declaring it in the derived class. Note that should we override a non-virtual function, we'll get an error. This works like magic. Now the base reference remembers that it was created from a derived object, and when we call the doSomething function, it calls the derived one. This is the core principle that enables dynamic polymorphism and object-oriented programming in C++. Now that we know that it works, let us dig a bit into how it is implemented under the hood. How does a reference remember that it was created from a derived object? And the answer is that it knows this by looking up the correct function to call in a virtual method table, or a vtable. The vtable is not magic. It is just a table of pointers to functions that can be queried by a function name. Let us extend our example a little to see what happens under the hood when we declare and call virtual functions. Whenever a compiler compiles a class that has any virtual functions, it creates a vtable for that class. and adds a hidden pointer member to the base of the corresponding class hierarchy, which makes sure that all the classes in the hierarchy have this vtable pointer. Now, if we create a derived object, its vtable pointer points to the vtable that corresponds to the derived class. The trick here is that even if we refer to this derived object by a base reference, this base reference still has the access to the vtable pointer as it actually is defined in the base class. So if we call the doSomething function through the base reference, or a pointer for that matter, the compiler knows that because it is a virtual function, we have to follow the vtable pointer to find the correct doSomething function in the vtable. In this case, derived doSomething, and call it. As a tiny exercise, think what will happen if we set the base ref to point to an object of base class instead. Comment below this video with your answer. This implementation is very neat, but there is no free lunch. We pay for this flexibility both with memory and the runtime overhead. As we've just discussed, every object of a class that has at least one virtual function must store a pointer to its vtable. That pointer occupies memory, usually 8 bytes. While it doesn't seem like much, it might become an issue if we need a lot of such objects. So much so that it might become a serious limitation. And speaking of limitations, as we've just mentioned, the selection of which function to call happens at runtime. That means that the compiler generally doesn't know which virtual function will be called, and so this limits its optimization capabilities. In addition to that, adding virtual functions to classes introduces some constraints on how we should use these classes, and creates a couple of pitfalls that we should be aware of. In the previous examples, we omitted quite some details, and it is time we cover those details now. Generally speaking, every class that has a virtual function must have a virtual destructor. Even though destructors are not inherited, if a base class declares its destructor virtual, the derived destructor always overrides it. The reason why this is important becomes easier to grasp once we move on from using references with our base and derived classes towards using pointers, especially owning ones. To properly understand why the destructor must be virtual, we have to answer the question: if we create a derived object and store it by a base pointer, which destructor will be called once we delete our object through this base pointer? Take a moment to think about it. Pause the video here if you need to, look at the examples we just covered, and remembering that a destructor is just another kind of function, really think about it. And I'm sure that you get it right. If the base destructor is not virtual, then this base destructor will be called. But this destructor knows nothing about the derived class.
You know nothing.
Base destructor. Which leads us, generally speaking, to an undefined behavior. And if the derived class has additional data, their memory is not freed, which is a memory leak. Now, if the destructor is virtual, a call to it will go through a vtable, and so the correct derived destructor will be called. So I hope that we see why we need a virtual destructor if we ever expect the object to be deleted by a pointer to its base class. But if you remember, we already talked about the rule of all or nothing, which states that if we need a single special function, like the destructor, that deals with the object's lifetime, we need all of them. This is true in this case too. Alongside a virtual destructor, we need to deal with the copy and move constructors and assignment operators. I believe that all of these special methods must be deleted, because classes with virtual methods are designed to be used through a pointer, meaning that they have pointer or reference semantics. They're not designed to be moved or copied, meaning they do not have value semantics. If we try to copy or move a class that is designed with pointers and references in mind, we run a good risk of slicing our object. Slicing happens when a copy or move constructor or an assignment operator is called on a base class when the actual allocated object was a derived class that has more data stored in it. The base class only knows how to copy its data, not the derived data. Putting this all together, a better way to implement our base and derived classes from before would be to add all the missing deleted special functions to the base class. And we'll also add a default constructor too, for a good measure. There is also a quicker way to do this by inheriting from a simple non-copyable class, which can be reused for any class that is not supposed to be copyable or movable. Then we just need a virtual destructor because all the rest of the special functions are already taken care of. It is also important to mention that for polymorphic classes, those that have a vtable pointer, just like we can upcast our type along the hierarchy of classes, we can downcast too For that, we use a dynamic cast, so it is an explicit cast. This is considered an anti-pattern though, and breaks the so-called Liskov substitution principle that, applied to C++, states that when we work with a pointer or a reference to base type, we should have no need to know which derived type is actually being used. If this principle is broken, the programs usually become more brittle, meaning that making changes to them without breaking things requires more work. That being said, it is probably still important to understand how dynamic cast works. Dynamic cast allows us to downcast a pointer or a reference of a polymorphic base class into a pointer or a reference of the derived class, derived from base. We won't go too much into detail, but it is important to know that this conversion might fail. If this conversion fails while converting a pointer, a null pointer will be returned, while if the failure occurs while converting a reference, a stood bad cast exception will be thrown. We're almost ready to return to our original image example and finish its implementation with all the best practices in mind. There is just one more thing to cover before that. In my experience, having virtual functions that have a base implementation and some overridden implementation in a derived class becomes confusing quite quickly. It becomes hard to find where in the class hierarchy the actual implementation lives, and I've spent hours and hours on this in codebases that had deep polymorphic object hierarchies. The solution is to separate interface inheritance and implementation inheritance altogether. You see, there is one more trick up our sleeves with virtual, the pure virtual functions. They allow us to define a virtual function that does not have any implementation by design and must be implemented by the descendants of the class it belongs to. This is perfect for creating interfaces. We generally call a class that has at least one pure virtual function an abstract class, and a class that has all of its functions as pure virtual an interface. In my experience, I prefer to make sure that if my class is abstract, it is an interface. This allows to keep a shallow hierarchy of concrete implementations of such interfaces. In combination with using composition and function reusing in the actual implementation, this allows us to have a hierarchy that is easy to read while avoiding code duplication. But do tell me your experience with all of this. What is your preference, if you have any? Speaking of keeping a shallow hierarchy, let's also briefly talk about the word final. We can use it to forbid any future extensions of a particular class. It is helpful when implementing a shallow hierarchy of classes that all implement pure interfaces, but I would suggest to be careful with the use of it, as it is very hard to know the future, and this is equivalent to a statement, "I'm 100% sure that nobody ever will need to extend this class," which is a hard statement to make confidently. For completeness, let's see how our polymorphic classes example changes if we follow all the practices we've just talked about. Here we change base to be an interface, add one more implementation class, another derived, and mark our derived implementations final to make sure nobody can build a deep hierarchy on top of them. We also convert the main to use pointers, just to show that we can refer to two different implementations by the same pointer. C++ also allows to use multiple inheritance, but do note that it is heavily discouraged in case of implementation inheritance. That being said, it is okay sometimes to use multiple inheritance when a class needs to implement multiple interfaces. It is easy to imagine that a game object can be both drawable and, say, movable. This allows us to separate the concerns in our design. The standalone functions move and draw need to know nothing about the objects being passed into them, as long as those correspond to the required interface, and our box satisfies both. Now we really know everything there is to know about inheritance in modern C++. We know how simple and a bit limited implementation inheritance is. We know that the interface inheritance enables dynamic polymorphism, we understand how it works under the hood, and we know the best practices related to creating and using interfaces. So it is time to put it all to a small test and get back to our original example with the image class. We can now properly implement the missing parts. We make use of the non-copyable base class to declare the I/O interface with the write and read functions along with the virtual destructor. Note that our functions are both const qualified as well as pure virtual. Then our JPEG I/O and PNG I/O implement the interface by overriding the write and read functions. The actual implementation is not important to understand inheritance, so they just print something to the terminal here. Finally, just as before, we use the reference to our interface in our image class to refer to any implementation that we pass into it in our main function. This, I believe, follows most of the current best practices when it comes to implementing an OOP-style system that relies on dynamic polymorphism. So I guess we can close this lecture with this example as the one that encapsulates everything that we covered today. And if you are interested in how to achieve very similar results with templates, please give a watch to the series of videos I recorded about templates, starting with why. Thanks a lot for your attention, and bye.